In chapter 13, we'll be looking at organic spectroscopy. Just to give you a brief background about the importance of this subject matter, you may be wondering, of the millions of organic compounds that exist, and every day new ones are being synthesized in the various labs, and new ones are being discovered every day from natural products. The question now becomes, how do we know what are the structures of these molecules? As you know, the structure of molecules, the bond-to-bond connectivity, the type functional groups that are present, that's very important if we are to carry out reactions on these molecules. Organic spectroscopy is used to determine the structure of organic molecules. So in this presentation, we'll first of all define spectroscopy, and we'll look at how it can be used, or more specifically, how it is used in organic chemistry to determine the structure of organic compounds, specifically unknown organic compounds. But before we do that, we'll do a little bit of background, and we look at the electromagnetic spectrum that deals with the energy that interacts with molecules. Then we will go into two types of spectroscopy in this lecture. The first is the ultraviolet spectroscopy and the infrared spectroscopy. So, as I have already mentioned, there are literally millions of different organic compounds, and new ones are being identified on a daily basis. But how is this identification carried out? The underlying principle here is that organic molecules, when exposed to energy, behave in a very predictable manner. The key word here is predictable manner. So each molecule will behave differently when it's exposed to different types of energy. And based on that behavior, we can get a good idea of various information about that molecule. So here we have different molecules here. As you know, this is a ketone, cyclopentanone, carboxylic acid, alcohol, and an ester. These four molecules will react with energy very differently. And based on these different reactions or interactions with these molecules, we will get specific information about these molecules, the structure of these molecules, and we can put those bits and pieces of information together to determine the structure of the molecule. So let us do a quick review of energy. This you have covered in your physics course, but as you know, energy travels at the speed of light, and there are some characteristics about energy, and the two important ones that we will be stressing in this course is the wavelength and the frequency, but primarily the wavelength. The wavelength, of course, as you know, is the distance from one crest to the other. That's the wavelength of the energy that's traveling. So, here's the electromagnetic spectrum. And of course, here is the relationship between wavelength and energy. So here is the wavelength that's 10 to the negative third in meters. That energy is described as the radio frequency. Less energy and radio frequency. The microwave has a frequency of 10 to the negative 2. Infrared, 10 to the negative 5. Notice it's getting shorter and shorter. Ultraviolet, 10 to the negative 8. Of course, as you know, you do not want to be exposed to the ultraviolet radiation for too long. Very short, much shorter than the visible. Here is the X-ray, even shorter, 10 to the negative 10. And the gamma ray, which is even shorter, is 10 to the negative 12. So this gives you the relationship of the wavelength of energy as broken down to give you different type descriptions. So here is an equation or a few equations that relate the energy to, in our case, we're mostly interested in the wavelength. As you can see here, there is an inverse relationship between the energy and the wavelength. It's inversely proportional, which means that if there is a high energy, the wavelength is pretty short. If there is not much energy, there's longer wavelength. So let us look at how this can be broken down to give you the effect on the molecule or the effects on molecules. Here is 10 to the negative 9, very short, that's the gamma ray. 10 to the negative 7, X-ray, very short. Ionization of molecules, that means it breaks the molecules apart. Here is the ultraviolet, a little longer, and there's some ionization, but electronic transition. So we'll look mostly at that in a special type spectroscopy that we'll look at shortly. The microwave, 10 to the negative 10, much longer, and that's described as the microwave. Notice the energy here is not as much as up in this region. The effect that the microwave energy has on molecules is the molecular rotation. So of course, as you know, in terms of heating the food, what it does is, because there is water present in the food, when you turn on the microwave, that energy is specific in that region here for that wavelength, and that causes molecular rotation of the water molecules, and that generates the heat that heats up the food. Here is the energy in a much longer wavelength, radio waves. Energy is much less, 10 to the negative 4 kilojoules per mole, and that's used for electronic spin transition in molecules. We'll do that when we do the nuclear magnetic resonance spectroscopy. So this gives you a summary of the energy as it relates to wavelength and their effects on molecules. Let us look now at energy in the ultraviolet region of the electromagnetic spectrum. As we said earlier, spectroscopy is the interaction of molecules with energy. So what we'll do here is we'll look at the interaction of molecules with energy in the ultraviolet region of the electromagnetic spectrum. The type molecules that interact with energy in this region are molecules that are unsaturated or are conjugated, double bonds. And let's see what happens. Remember here that double bonds, unsaturated double bonds, contain pi electrons from the pi bond. It does not affect the sigma bond or the carbon-carbon single bond, just the pi bonds or the double bonds. So the simplest double bond that we have is ethylene, CH2CH2. Here's a pi bond right here. So what happens here is, if you look at the pi bond, there are two. One is the pi 1 and one is the pi 2. In the ground state, before excitation, before the energy hits, the electrons, the two electrons are in the ground state, in what's called the highest occupied molecular orbitals. When energy hits this molecule in the ultraviolet region, and more specifically in that energy region, there is an excitation to the LUMO, which is the lowest unoccupied molecular orbital. This energy is specific, and that causes excitation, and that's the type interaction. So based on that excitation, one could tell that this molecule has a double bond present. So let us look here at some other systems. So here is isoprene. It has a lambda or wavelength of 222 nanometers. That's the energy required for excitation, for the pi electron to go from the HOMO into the LUMO. Here is 1,3-butadiene, has 2 double bonds in conjugation, and it requires that energy. Of course, the energy is now expressed as wavelength, lambda max. Max here means the exact point at which that transition occurs. Notice that they're very similar. Very similar, 222 and 217. Why? Because they are conjugated and it's just 2 double bonds in conjugation. So if there is an excitation in this region of the ultraviolet spectrum, we know that we have a double bond in conjugation, or 2 double bonds in conjugation. Let's look at this system here. 1,3,5-hexatriene, 1, 2, and 3 double bonds that are now in conjugation. Notice here it's a longer wavelength, less energy for excitation, because the energy required for excitation for this molecule is different from this molecule. We can tell that these two molecules are different if they were unknown in the UV spectrometer or spectroscopy. Okay, here is what the UV vis spectrum looks like. So there is a scan. The machine automatically scans the wavelength in terms of energy. So it goes from a low to a high wavelength. or longer wavelength, less energy. If the unknown is isoprene, for example, or if the unknown has 1, 2 double bonds in conjugation, there is a signal in this region right here. And of course, as we know, as we have seen from the previous slide, that lambda max, lambda here means wavelength, is around 220, 222 nanometers. So that's how UV spectroscopy is used to determine, give some information about unknown compounds. It tells us the extent of conjugation within a molecule. Some terms that are used here: chromophore, that's the unsaturated region in a molecule that gives rise to electronic absorption or electronic transition, or a signal in the UV vis spectrometer. It could be a double bond, it could be a carbonyl, it could be a nitric group, or it could be conjugated double bonds. As you'll see in your textbook, there are different type molecules that have different lambda maxes, and that gives us an information about the structure of the molecule. Another term that is typically used in UV spectroscopy is the bathychromic shift, which means there's a shift to a longer wavelength, a red shift. So of course, as you know, in chemistry we have these terms that we use: a red shift, a bathychromic shift, shift to a longer wavelength or shorter or less energy. Hypsochromic shift is the opposite, shift to a shorter wavelength, or a blue shift. Again, just some terms that are used especially by spectroscopists. Let us now turn our attention to the infrared spectroscopy. Infrared. This means that we'll be looking now at what happens to a molecule when it's exposed to energy in the infrared region of the electromagnetic spectrum. What happens here is that there is a predictable interaction. In this case, however, it is not electronic excitation, but it is the vibration of bonds. So as you know, here is a molecule down here. All the atoms are connected by bonds. In the infrared spectroscopy, or in the region of the infrared energy, these bonds vibrate. All the bonds start to vibrate, but the vibrations will occur at different frequencies, and that is how we can tell the difference between this molecule, for example, leucine, with this molecule, aspirin, from this molecule here, because the bonds here vibrate differently, and it requires different energies for this specific bond vibration. So let's see how it works. So covalent bond of an organic molecule is connected by two atoms, as shown here, 1 and 2. Here's a spring that's used to illustrate the bond. In the region of the electromagnetic spectrum, or if energy in the infrared region of the electromagnetic spectrum interacts with this molecule, it stretches. So that's a vibration, that's a stretch vibration. So based on that energy that's absorbed for this stretch, we get some information about this bond here. So let us look at a real molecule. So as you know, there are different vibrational modes. So if the molecule is a linear molecule, as we've seen here, we can calculate the number of vibrational modes using this equation. There are 3n minus 5 vibrational modes, or 3n minus 5 different ways that this linear molecule can vibrate. N here represents the number of atoms in the molecule. So carbon dioxide, of course, as you know, is a linear molecule, as shown here. Using the equation above, we have 4 vibrational modes. So there are 4 vibrational modes, and the key here is that each vibrational mode will require a specific energy from the infrared region of the electromagnetic spectrum for this excitation. So here are the 4 vibrational modes of carbon dioxide. There is a stretch, like we have seen here. This bond can stretch here. This bond can stretch here, as shown here, whereas this one can go out. That's a different vibrational mode. Notice the energy that's required here. It's 1340 Cm-1 for the energy requirement. Here is the energy requirement for that vibrational mode. Here's another one. This one is going out, and these are going back. Another type vibrational mode requires a different specific energy for that vibrational mode. This one here is pretty similar, but it's a different vibrational mode, and it requires energy in the same region of the electromagnetic spectrum. So what is expected here if you should expose carbon dioxide to infrared radiation or infrared energy from the electromagnetic spectrum? What you'd expect to see is a signal for each vibrational mode here, or something happens at these different points here. So let us look at the actual spectrum. So here's the actual spectrum of carbon dioxide. So this is water contamination. It's very difficult to get water out of a pure sample, so it's present, but here are the vibration modes. Here is the ones at 1700, and here's the other one at 666 in the 600 region. They overlap, but here are the vibrational modes for carbon dioxide, and this now represents the infrared spectrum of carbon dioxide. So if you have an unknown compound and you put it in the infrared spectrometer, you would get a spectrum looking like this and only like this for carbon dioxide. So this gives you an indication that the unknown compound is carbon dioxide because it has a spectrum looking like this in the infrared region. Let us look at water. Water, as you can see here, is a non-linear molecule. The equation that's used to calculate the vibrational mode is 3n minus 6, where n represents the number of atoms. So if doing the calculations, you can see there are 3 modes, 3 ways that water can vibrate at different frequencies, and at these different frequencies there are specific energy requirement for for these vibrations. So as you can expect, if these vibrations are different in energy requirement compared to carbon dioxide, the spectrum of water should look different from the spectrum of carbon dioxide. Here's a spectrum of water, very different from the spectrum of carbon dioxide. So here are the three stretch modes, or the vibrational modes. Here's the scissors mode, 1885. Here it is. And this is an illustration of that vibrational mode. As you can imagine, it's like a scissors going in and out. That's what happens when energy hits it in this region of the electromagnetic spectrum, 1885 Cm-1. Here's the other one, asymmetric stretch. So it goes here and here in asymmetrically, 3500. Here's the symmetric stretch, 3585. Notice they occur in the same region, and that's why we have such a very large absorption band here for these two excitations. Notice the excitations here are not electronic transitions. These are excitations based on different vibrational modes of the different bonds of the molecule. As you can imagine, these are two very simple molecules which contain 3 atoms: carbon dioxide, carbon, 2 oxygens, water, oxygen, and 2 hydrogens. So the spectrum here is very simple, but as you can imagine, as we get into larger molecules where there are a number more vibrations, you will see a number of different type signals. So let's look at some examples. So the infrared spectroscopy is used primarily to identify functional groups. As you can imagine, there are a number of carbon-carbon bonds, carbon-hydrogen bonds, so there are umpteen different vibrations. But the ones that are of importance to us in organic chemistry in terms of structure determination will be the functional group. So here the alkyne, it will have a frequency of 3300 in that region. So if you do your infrared spectrum and you get a band or an absorption or a signal in this region, there's a strong indication that it's a carbon-carbon triple bond. Here's another one, aldehyde, around 1700, 1740. Carbonyl for the ketone, in the same region but slightly different. So if you have a very sensitive instrument, you should be able to tell the difference between the carbon-oxygen double bond vibration for the ketone compared to the aldehyde. Same for the ester. Again, notice a little different here, even though they are in the same region. Same for the carboxylic acid. So it's possible to tell what functional groups are present in a molecule based on the signals that appear in the infrared spectrum. The OH is a very prominent one if it exists in a molecule, and it exists around 3600, 3650. The NH is another prominent one. It exists around 3000. And of course, as you know from organic chemistry, there are different types of amines, primary, secondary, and tertiary. So again, if you have a very sensitive infrared spectrometer, you should be able to tell what type amide exists if it has a signal in that region. Here's another functional group. Nitrile has a vibration in that region. This is just a small portion of that table in your textbook. There are other functional groups that are present. So look at that table and have it present whenever you are solving the structure of unknown compounds using infrared spectroscopy. Let us look at some examples that are a little more complex. As you can see, this spectrum here is a lot more complex compared to that of carbon dioxide or water. This is benzoic acid. The functional group present here is the carboxylic acid. But let us take the approach of analyzing the infrared spectrum first. There's a band in this region around 31, 32, 3300. Looking at the table of functional groups for the IR, that frequency indicates an OH. So we know in this molecule, if it were an unknown, would have an OH present. Here's another prominent bond, another prominent band here, and this is around 1720, and it's an indication of a carbon-oxygen double bond. So we know that this spectrum here, based on this band and this band here, is a carboxylic acid. We'll use another type spectroscopy to learn that this group is present, and hence we know that this unknown is benzoic acid. Here's another example. Here's benzylamine. Notice again that there is no band in the region of 1700, which means that there is no carbonyl present in this compound if it were an unknown. So looking at the spectrum again, we see a band here, and that indicates the presence of an amine. Two bands here overlapping or pretty close to each other would indicate the presence of the vibration of a primary amine, the two NHs of a primary amine. So again, if this were an unknown compound, since there's no band at 1700, but there's one in this region, it's a strong indication that it's not a carboxylic acid, as we have seen before, but an indication of an amine. Notice for the infrared spectroscopy and for the UV-vis spectroscopy, we're getting bits and pieces of information about the molecule. Eventually, we'll put it together to determine the structure of the unknown molecule. Here's another one. This is, so again, let us look at the spectrum first. There is no band in this region, but there's a band at 1700, around 1700. That's again an indication of the carbon-oxygen double bond. This bond is very prominent, and that's typically the CH bond. You'll see it for just about all organic molecules. But again, there is no band in this region, which would indicate that it's not a carboxylic acid, it's not an alcohol, and it's not an amine, or primary or secondary amine. Here's another example. Again, this one does not have a band at 1700, but it has a band in this region here of 30, what's that? That's about 3500. Again, an indication of the OH bond. We know it's an alcohol and not a carboxylic acid because there is no carbonyl bond in this region of 1700. So hopefully you can get from this infrared spectroscopy, by looking at the prominent bands here, you can get an indication of the functional groups that are present. By looking at the bands that are not present, you can get a good estimation or good assumption what groups are not present in this unknown. This is the end of this lecture for the first part of chapter 13 for spectroscopy. We looked at infrared spectroscopy and ultraviolet spectroscopy. Our next lecture will cover the others, mass spectroscopy and NMR. So look out for that. But continue reading the material in the text and solving the problems so that you can appropriately apply the concepts that are covered here. Okay?